the idea of magnetic force is very similar to a gravitational force and electric force. So let's reiterate about all of our fields in the year. We started with the gravitational field, which provides some pull toward the ground, which gives you your weight, right? Or the force due to gravity. Then we looked at an electric field, and we determined there's an electric force between two charged particles. And now we've looked at magnetic fields, and we're going to talk about the force felt on a charged particle in a magnetic field. Okay? The force felt by a charged particle in a magnetic field. So our two objectives are to determine the force or strength of a magnetic field. And they're two different things. The force and the strength are both different. And we're going to find the direction of the force on a charge moving through a magnetic field. Moving through a magnetic field. Okay, so two things. We're going to do a different right-hand rule today. It's different from yesterday's. It's going to help us with the direction which a particle would move and the force is felt. So, first, you don't have to write this, okay? You don't have to write this. I just wanted to add it up here so we can just read from it. Can somebody read for me, please? Next.
From experimentation, it is seen that a stationary charged particle does not interact with a constant magnetic field that a moving charged particle does. Charging particle does.
Oh, it's just the charge. You're right.
The force experienced has a maximum value when the charge moves perpendicular to the field, decreases at other angles, and is zero when the particles move. Particles move.
Oh, jeez.
We will play that night?
No, I'm not going to read this.
Hi, bad guys.
Parallel to the field line.
Alright. So, the idea is this. If you're standing in a gravitational field, you feel your weight. But if a charged particle is in a magnetic field, it doesn't feel a force unless it's moving. So if there's a charged particle somewhere and it's stationary and being held at a certain position and not moving, even if it's in a magnetic field, it's not going to feel a force on it. It's going to be as if there's no force at all. And this was discovered experimentally. So there's no theory behind why this happens right now. It's just experimental evidence. Okay? But when a particle is, projected through a magnetic field, how a TV works, old TVs, not anymore. When old TVs had a deck to them, they had what's called a cathode ray tube in them, which was really a beam of electrons that was sent through a magnetic field. That's what gave you a cathode ray tube, it's called.
Was it from cathode from chemistry?
Cathode and anode.
Biology.
From chemistry, not chemistry. Has to do with positive or negative polarization. Cathode and anode, So, the cathode ray tube would send a beam of electrons, charged particles, through a magnetic field. It felt the force, sent those to this phosphorus screen, which gave it light. That's how TV used to work, and that's really one of the major applications of this. Okay, now they're different, obviously, but it was discovered experimentally. That's the key here. Now, with that said, we have a formula we're going to look at. And the formula is as follows. And this is the magnitude of a magnetic field formula. B, which is the magnetic field strength. B, which is the magnetic field strength, equals, I put F mag for magnetic, okay? Now, your last formula was FE, the one before there was FG, you're always going to have subscripts, okay? I was going to put FM, depends, I just want magnetic because M could stand for other things in physics. QV, what does Q stand for? What does Q stand for? Who remembers? The units are coulombs. So what does it stand for though, Paul?
Isn't that constant?
Sometimes it's a constant. If you have a proton or an electron, it is a constant. But tell me the term it is. What is Q?
The charge.
The charge on the particle. Again, this is the magnetic force felt, which is like your weight, Fg, the gravitational force felt. This is the magnetic force felt up there. And what is V for?
Velocity.
Yes, because the particle has to be moving, right? Molly, you know how else you could have told, right? Look at the units, right?
Oh, yeah.
Again, people, look at your units here. Newton is a force, coulomb is a charge, meter per second is velocity. T stands stands for Tesla. T stands for Tesla. Those are the units of magnetic field strength. Tesla. Fernando. Why does it need to be moving? That was the thing I said before. It was discovered experimentally. There's no reasoning for it anymore.
Right, I know you said that, there's no reason behind it at all.
Go research it. Tell me. See if you can figure it out. I tried to actually look it up, but I couldn't. There's nothing on it. It's just discovered experimentally.
That passage yesterday that Rachel was reading, that's like my mom basically.
No way.
Like she's like constantly like going like staying away from the microwave and like all this ridiculous. Like she literally does not let me put a computer or an object
On your lap.
on my
You
lap.
shouldn't.
It's
You
just
never, guys, especially.
crazy.
The heat one.
Especially.
I heard that. I think everybody knows.
My cat
Like the heat is bad, and then the radiation, yeah.
I don't
Well, the
want
other thing is this, like your phone, I told you guys this, what should you do when you use your phone?
Oh, but that has to be your
Don't
problem.
put it in your bag.
Well, that's one thing, but what should you do when you use it?
Oh, you can't put it, you can't sleep next to it, or like you can't put it next to your head when you're speaking to it, apparently.
Yeah, you shouldn't do this.
Yeah,
What you should do is this, literally, just that. The little, like, 1 centimeter distance is exponential. The amount of radiation between these is over R squared.
I use my head.
So if you just go like this a little bit,
Like this,
Hey, that's not
right
Can you hear stuff?
No.
Hang on a second, I don't want to get cancer. I don't know if
What if
I have a question.
Say that again.
Does
Straighten out
the
a lot of
gas
computers.
let have a
What
greater?
is the attitude?
Wait, we're talking about cancer.
If you move these up, watch, move these up. The faster it moves, the higher the force is. But the faster it moves in a field, it just doesn't affect the
Wait,
field.
does standing in front of a microwave actually like?
If you did it enough, yes.
I don't.
If you did it
I
enough.
don't feel like recreation.
No, but doesn't those,
Tyson, that's really good to know. You don't do that recreationally.
I mean, sometimes I'll just like stand.
wait, is it?
Hey, what are you doing tonight? Nah, I'm just chilling in front of the microwave, actually. Okay.
I'm just talking on the phone next to my microwave.
With my computer,
My son's my computer on my
With
back.
your computer on my lap.
The right-hand rule for magnetic force says the following. You take your thumb in the direction of the velocity of the particle. So if it says the particle is moving up from the ground, start like that. Then if it says that the magnetic field is directed east, isn't that way? For you guys, east? So it looks like that,
This is that way.
right? East is that way.
No, if you go over there,
Not in the city, where you're sitting.
Big elephant can't
Guys, not in the city right now, from where your orientation is. If you were thinking, that's north, east, west, south, just imagine that, okay? So, the particle is moving up from the ground,
I thought you said me.
up from the ground. Guys,
Up to the ground,
Wait, up to you.
to the east
to east.
is to the right, tells you that coming out of your palm is the direction of the force of the field, which would be into the page. See this right here? Into the page, from my perspective.
Into the,
If it said the particle was moving, let's say the
Wherever your
particle.
palm is open to, that's what the magnetic field is.
Correct. The palm indicates the magnetic field's force direction.
But that.
Jeff, hold on. Let's rephrase that. Guys, stop. Listen. The magnetic field is B, Jeff. The force felt is low. Okay, the force felt. So if you had a problem where the particle was moving east now, the particle was moving east, what does that mean you do? Good. Start by putting your thumb to the east. Then it says the force or the magnetic field is acting south. You gotta go like this, right? Particle east, magnetic field south. So which way is the force acting again?
perpendicular.
Right hand, Jeff. Left hand, cage left hand. There you go.
Okay.
So it's acting again into the page.
What about
Same direction there. So depending on what it says, you have to orient your hand to see which way it's moving. It works well every time. You just gotta practice it. Okay? Try this one. Only right hand, no left hand, no left hand.
Guys, here's a test note that I killed.
Practice, ready?
in the shower?
So the velocity
I did that.
is, the velocity is,
Don't act it. Don't act it.
guys, stop talking. Velocity is down, stop.
Too far.
The field, you're very close to being asked to leave. Don't say that ever again. The field is west. Find the direction of the force. The velocity is down. The field is west. Which way is the force going to be acting?
Velocity is down.
And you don't have to say it, just do it with your hand. Velocity is down, so start with your thumb down. Thumb goes down. You go either way, right? So then the field is west. Which way is west? West is that way, right? So velocity is down, field is west. Okay, velocity is the thumb down, field is west, over. So which way is the force acting?
What if it was north? None of this?
You can't, well let's see, if you have the velocity down, could the field be north? No. The velocity and the field can never be opposite directions of each other. They must always be perpendicular to each other. See this right here? This perpendicularity right here. Okay? The velocity and the field must always be perpendicular. It's a good question. So the velocity is down, field is west. Which way is your palm face? Into the...
North.
What do you say this way? Into the what? Into the page. This would be what?
East.
No. What would the field be?
East.
Wait, what are you asking?
That would be.
The field this way is into the page, right?
Yeah, back away.
What would the field this way be called?
Away from the.
Out of the
Well,
page
that's
or away from the
Well,
page.
that's
We
the
say
way.
south.
Okay? That would be if it was traveling velocity south
Velocity
and field east.
With velocity down.
Velocity south or down, sorry, thank you, down.
Wait, are we
And
not
field
allowed to
east.
say, let's say you say that the velocity down is south. Are we not allowed to use south as palm again?
Wait, can we do about more?
You can ask that.
Palm.
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 Is it palm or palm?
Palm. Imagine
Palm.
POM.
Palm.
Say POM. How would you say it?
Palm.
Then you say orange
Palm.
or orange. You can say or orange.
Or Jordan.
Orange.
Anyway,
Or
they're always going to be at right angles.
No, you know what I'm asking though? Is
Say
like,
crayon.
they were saying away from the page and from the page, we could say
Sounds
south
like
and north.
crayon.
Right.
Because that would be south, that would be north.
No, this is north, this is
Oh.
south, this is west, this is east. This is into the page, this is out of the
So
page.
on the test, what are we supposed to say, like?
Into the page or out of the page. Oh, yeah. No, you do, physics, yeah. So you know what I can say? Watch, ready this. The velocity is out of the page. So start by doing this. Coming towards you out of the page.
This is side of the page.
This is into the page. Guys, again, ready? Here's your directions.
Side of the page?
Into the page, out of the page, west, east, north, south. That's all you know. Now, velocity is into the page, so start with your thumb going into the page. And let's say that the field is spelled north. So put the field up for north. The force must go east. Okay? Velocity is in the page. Field is north. Force is spelled to the east. Okay? It can be any of these orientations, doesn't matter. How about this one, ready? Trick it up a little bit. The force, I'm telling you the force now, which is what?
This
The palm. The force is spelled into the page.
So
how you
how
start.
is it? So how is it?
Okay?
So that means that it's way west and
The force is into the page. The velocity is down. So which way is the field?
up.
It's west, west.
But doesn't the palm, doesn't
No curl. No curl.
Wait, but
Guys,
how do
the
you?
curl is when
Oh,
you're
it
in the
depends on
field.
what hand you use.
So it's always in my hand. That's what.
Oh.
Oh.
Wow, that makes sense.
You can be given 2 or 3. Doesn't matter which 2.
So the
Alright.
Venus magnetic field, it's no
And there's no curl. That's your fingertips.
curl.
That's because it's not a magnetic field this way. It's a direct field. Sure, you can think of it that way, Jack, but it's different. We're not talking about a magnetic field from a magnet. Now we're talking about a field that you're in and has parallel lines. Remember the solenoid? Remember the solenoid yesterday? With the field going through the inside of the channel? That's what this B is.
You need to read that?
Max, write it down, please. Those of you with the notes, obviously, just hang tight. Write down your givens that you already have written down here. Write down your givens, and after that, go ahead and start looking at your formulas.
Oh no.
I'll write down the things,
You should load the slides next year.
Load the side
You know
and then
who?
right.
You know who's in the group next
That's fine, you can answer it.
Like, I'm just gonna-
Snap, once or twice.
Guys, I encourage you to use the slides and not my notes. You sitting there reading, okay, is not as good as you actually writing. So if you're going to use an iPad, that's good, but please use the slides. That's why I put them up there. So proton moves straight upward. So that means up. Straight upward, okay? From the ground now. Which is, in our sense, we could say like north, right? Is moving straight upwards. So we know that that's the thumb already. Thumb is up. Through a uniform magnetic field that points east. Which way is east? Which way is east?
Right.
Alright. So that's what we have, right? So which way is the force going to be felt?
Into the page.
Into the page. Again, this is up, this is east, the force is into the page.
Velocity is north.
Okay, velocity is north. I put away from the ground, upward.
Are we doing the math part of it?
Yeah, so now we have to figure out if the proton moves at a certain speed through this field, what force, magnitude, and direction, so we've tried to find the direction, will act on it. So let's start with our givens here. Givens, who's got them? Jeff.
Okay, so T tells you.
Good is the what value? What variable?
That's your B.
Good.
So that's your magnetic field.
Very good. Strength.
That's your fingers.
Good. That's your fingertips.
And then your speed. I mean, that's this
Velocity.
Velocity 2 times 10 to the 8th.
Is your what?
That's on the bottom part. Below the denominator.
But what is that with your hand? That's your
thumb.
your thumb. Good.
And then you're searching for the magnetic, the FMG, MAG.
Yeah. Now, one question is this though. Here's the formula.
E equals. So we're solving for it. You have to switch. What you can do is you can switch the QV and the
With?
B. So then you just do the diagonal switch, and you end up getting QV equals F over B.
But then you got to move the b back up to get f by itself anyway. So leave the b alone. Leave the b up here. Just move this up. Jeff.
Oh yeah, that's what we're solving for.
Okay.
So then just multiply by QV.
Yeah. So multiply by qv. But that tells me I need a q, don't I? Anybody notice that we don't have a q?
Q is 1.6 times 10 to the negative 19.
Very good.
Very good.
Elementary charge on a proton is 1.6 times 10 to the negative 19. Okay? So let's write that down as well. And now you're just multiplying those three numbers. Multiply across. 3 times 1.6 times 10 to the negative 19 times 2 times 10 to the 8. You're going to get a very small force, which is fine, because the magnetic force is at a molecular level. So this is the force felt by one single proton. One proton is doing this force. That's a lot of force for a proton to handle. It'd be like saying, imagine like a big bodybuilder, like 300 pounds. To feel a force of like 200 pounds to lift up is pretty easy, right? But then imagine like a 2-year-old. 200 pounds is a lot for a 2-year-old, right? Same idea here. Okay? The force is very small because of the object here. It is significant though. It is significant.
Yeah, can we switch 2 times 10 to the 8th?
What do you mean?
That's like a normal number. Which would be
No. It's going to be like 200,000. I wouldn't do that. It's too big, yeah. Okay, multiply across, please. What do you get? What do you get? Come on, guys. We've made, not just you, Jeff, everybody should have a calculator. Let's go.
I got it.
Good, Joey. What do you got?
96 to the 11.
Good, very good. Okay? Very small force felt. Now, what should I put after that? The direction. That's the magnitude. A lot of you have been asking that question. I went over this in the beginning of the year. Maybe the first chapter we did. Magnitude is the amount. Direction is the direction. Okay? So when it says, what is the magnitude of the force? That is the magnitude of the force. What is the direction, though? We said the velocity was above the ground. We said that the field was acting east. So it's into the gauge.
So it's in the page with a force of 9.6. Just 10 to the negative 8. Are you gonna like?
Now, you could have also answered this question, believe it or not, with a north answer. And here's why. If you're standing on a globe, and say this is the North Pole up here, and this is the South Pole down there, and I'm standing here, and I think to myself, all right, velocity is coming out of the ground, so this is the globe right here. It's coming out of the ground, and the field is acting east, then this points up, which is toward the North Pole. So you could also set north there. Either answer is acceptable. I personally use into the page and out of the page, but your book will probably, or will possibly use north, south, east, west, and some of those answers also. But again, if you're standing here, and the velocity is out of the ground, that's like out of the earth. Here's the earth right here. East is that way, it's got to be north on the earth. Okay? Any questions on this? Here's a question for you, a follow-up. What would happen, or how would this be different if it were an electron instead of a proton? How would it be different? Fernando,
It would be negative.
what does that mean?
It wouldn't, because an electron is a negative charge.
Okay.
It wouldn't change. It would be, we disregard the negative charges. It would be the same.
You could disregard it if you take into account the negative affects the direction. So what would you do with the force?
So it would be the opposite direction.
So instead of into the page, it would be
Out of the page.
out of the page. Again, an electron, write this down, a negative charge travels opposite of whatever you get from the right-hand rule. So the right-hand rule applies to only positive charges. Whatever you get for the right-hand rule, switch it if you have a negative charge. Okay? Again, if you have a negative charge, switch your answer of direction for the right-hand rule. All right, this is what I find really interesting, this next part. And it's kind of cool because what we're going to do is we're going to relate circular motion and centrifugal force from way earlier in the year. Remember mv squared over r. We're going to relate that to what we're doing now. So take a look here. Imagine this is an electric field. Now, let me discuss two things real quick. A field into the page is represented with an X. A field out of the page is represented with a dot. So if you see, it's like an arrow tail. Imagine if an arrow was flying into the page. Wouldn't you see the feathers at the end of the arrow? Guys, take an arrow, right? Straight it back, shoot it into the page. You'd see the feathers at the end of the tail. That means into the page. If an arrow was shot at you, what would you see? The tip, right? Which is a dot. That's that point right there. Now, relax. Now, at this point in time, we have two options. So this one is into the page. So you start, take your fingertips, because it's the B, remember, into the page. So start with the B end of the page. Which way is the velocity? Up. So, we have this now. Into the page with the fingertips, velocity's up. So the force has to act to the right. You see that right there?
Yeah.
Now watch what happens though. If there's a force pulling it to the left there, it's going to go like this, right? My hand's going to start to turn. Because it's pulling it over. And then it turns more. And what's happening to the force no matter where I am?
It's going to stay the exact same length.
Okay, it's always acting which way? Toward the
Towards the left.
Towards the stop.
Center.
toward the
Center.
center. You say dot?
Yeah.
You said like stop.
Oh, sorry.
Toward the dot. Look. No matter where I am, watch.
But that's why it's exactly the same length.
And it will, that's very good, Max. It will remain the same length there. It's going to go in circular motion. So what we're going to see is it's going to act toward the middle, which causes it to kind of curl. And the more it curls, the more it acts toward the middle. So it keeps it in circular motion. So what we have here is an example, is what you should write down, where the centripetal force is provided by the magnetic force. The centripetal force is provided by the magnetic force. It's provided by the magnetic force. Now, anybody remember early in the year we made a table of different scenarios where we have circular motion and what provided the centripetal force? What keeps the planet in motion? What force? The force of what? Gravity. What keeps a car around a racetrack? The force of?
Inertia.
Not inertia.
The
A car going on a racetrack. Friction of the tires. What keeps a lasso in motion when a cowboy swings?
Centripetal. Gravity.
Not centripetal, not pull. Force of? Tension. The tension in the rope. So remember, the centripetal force was provided by many different things. Now the centripetal force is supplied by the magnetic force.
Only.
Only the magnetic force, that's keeping it in motion. Okay? So, what can we say from this? Magnetic force, as we solved in the last equation, was BQV. Agreed?
Yes.
Centripetal force formula is mv squared over r. That's what we've done all year, we use this. Therefore, since the centripetal force is the magnetic force, what can we do to these equations?
You could
Combine.
Yeah, exactly. Great, Jeff. Combine them, Jack. Good. Substitute and combine them. Both of you guys. Very correct there. Both.
So do you
Wait,
plug
when
in?
did we use centripetal force? When did I learn centripetal force?
Sure we did. Right here, mv squared over r. Go back and look at your notes. We did. No.
Wait, what do you? Oh.
So what
plug
happened?
in.
We don't know what to plug in yet. We'll see the problem in a minute. But what's going to happen here? What's going to cancel?
V's.
One of the v's on both sides, which gives me an equation of BQ equals mv over r. You're not going to be given this equation, but if you're told that an electron is in circular motion or a proton is in circular motion, you need to know that these two formulas, which are given, these are both given. Both of these are given on the test, are the same now, because the centripetal force is the magnetic force. They're the same thing in this problem. So you set them equal to each other, and you can cancel off one of these v's on each side.
Wait, wouldn't you make it m squared, not mv over?
There's no square. There is a square. It's not parentheses, Jeff. You don't have to have parentheses around the whole thing here.
I'm confused. Is that it?
The v is square only. The m is not square.
Oh, that's what I'm confused.
Okay? Let's take a look at the last problem. We'll finish this one up for the day. Now, one thing I want to iterate or tell you real quick, your book goes on to talk about magnetic force in a current carrying wire. Okay, I'm not going to go into that. We're not going to cover that one topic. So this section, we did like the first half, but this thing we're doing now, this is not in your book. This is a far more important. Okay, I'd rather you learn this part. It's on your SAT subject test, and it's something that will come up. Projectiles of protons and electrons in magnetic fields. When I was in AP Physics in high school, our school had AP-B and AP-C. AP-B meant there was no calculus in it, but it was a full year course. You did mechanics and then you did electricity and magnetism like we're doing, but at like an AP level they call it. Now, AP-C is only doing one or the other, mechanics or ENM. So our school, we have AP-C because there's calculus involved in it, and they do only mechanics. When I took AP-B, this kind of a question was one of the questions on one of those tests. Okay? A proton or an electron is fired through a magnetic field. You have to find the final velocity of it, then use that velocity and use projectile motion to see how far it went. Okay? Remember, if you know the velocities and stuff and the height of the projectile, so you could have a ray gun where you shoot an electron out of it. If you know the initial velocity, the velocity which it's turning with, you can see when it's going to hit the ground. Okay? So these kind of problems are very useful. A proton with a mass, I'm giving you the mass because I don't expect you to memorize that. With the mass of 1.7 times 10 to the negative 27 is moving through a magnetic field with 2.5 Tesla.
Wait, so since you give us the Q, are we multiplying the 1.7 by 1.6? You understand what I'm asking?
I would keep them separate for now, Jeff. Hold on, you're jumping ahead. Okay, we want to stay together here. If its velocity is 2.5 times 10 to the 7, determine the radius of curvature of the path it follows. So let's go ahead and set those equations equal again. Or let's write our givens, let's write our givens. Q is given on your formula sheet. Remember, it's at the bottom of the formula sheet. It says E equals. And E stands for elementary charge. Okay? So those are our givens in this problem. And what are we looking for? Good. Does everybody understand that? Does that make sense so far?
Yeah.
And we use our units to help us always. The units work. We have percent, kilograms, Tesla, coulombs. Jeff.
So when the question is asking not for like the force of magnetic field is right whenever it says like determine the radius of the curvature, then we're going to use the centripetal force combination.
Yeah, when it's asking for curvature or a path of a circular motion, you're using that formula and you're setting them equal. Okay, that's your indicating factor. So again, mv squared over r equals bqv. So mv over r equals bq. That's what we had last time. What are we trying to find?
R.
So what does it become? R equals what variables? How do we get r by itself? Good?
MV over BQ.
Good. Okay? So remember, switch the R and the BQ. You can always do that. You can always switch diagonally. So take this and flip-flop them, please. The whole quantity. BQ goes under, R comes up. Because now we have R alone in the numerator by itself. Plug in your values, please. Go ahead and plug in for M, V, B, and Q. I highly recommend that you put a major set of parentheses around your numerators and denominators. Okay, so this. So in your calculator, you're going to have a decent amount of parentheses sets going on here. Express your answer in centimeters, please. You're going to get an answer in meters, obviously, because you're getting radius. But I want you to convert it to centimeters, please.
Wait, it's not 2.72.
Check your numbers again in the back. Does anyone have a design for me that didn't turn in already?
Oh.
You're about to.
Alright.
They do today, so I'm fine. I think it's today. Anyone else?
That's me and Fernando.
Perfect. Is that you? You're Fernando? I didn't know that. Thanks.
Yes, yes.
Funny that's true.
Anybody got an answer for me? Come on. Too slow, people. Too slow. Let's go.
That's so funny. I didn't determine.
The answer that you're going to get here is 0.106. That's in meters. Convert to centimeters. Centi's 100, so move 2 spots to the right. You get 10.6 centimeters. So that's a radius of about this far. So you have an electron moving in a path like this right now. Okay? 10.6 centimeter radius path. Please write down the homework. This weekend I'll get back to you on your designs and give you comments so you can start building them and testing.